Modern video content typically goes through multiple format changes before anyone watches it. Videos come out of the camera as HEVC files. When you drag your footage into editing software, it might be converted to ProRes proxy. Then the editor exports it to H.264 for the YouTube upload. But before it reaches your viewers' devices, YouTube converts it again to a V1. The same footage gets converted many times throughout the production. It's all digital video, so one might assume we will eventually figure out the one best video format, and then everyone can just use that one. But in practice, every part of the process needs something different, so no single format can do the whole job. In this video, we'll learn why video format is actually two independent systems bolted together. A codec, which compresses the pixels, and a container, which combines the video and audio data into a deliverable package. Every frustrating mystery in video work can be explained by how these two layers interact. And by the end of this video, you'll understand how video professionals choose the formats they use. You probably know that .jpeg files are compressed photos that may have quality artifacts, and .png is for high-quality lossless images. With videos, it doesn't quite work like that. And the reason for this is really quite simple. Imagine you have a camera and an audio recorder. You record some footage, and when you're done, you now have two separate files: the video stream from the camera and the audio from the recorder. Conversely, whoever is going to view your content has two output devices, a monitor for video and speakers for audio. You could just send them the two files separately, but then the receiver's computer wouldn't know how to keep the lip sync perfectly aligned. So what we do instead is combine them into a single package, which contains the video, the audio, and timing information to keep them perfectly synchronized. Then you only have to send this one single file, and the receiver's computer breaks the package apart and routes the pieces to the screen and the speakers. This thing in the middle is the container, and when your friend looks at the file you sent them, they don't see the video and the audio as separate tracks. They only see the extension of this container. Notice how this packaging changed the file extension, but the underlying video data stayed the same. So this is why you cannot tell anything about a video's quality based on the file extension alone. The part that really decides the picture quality is the codec. A single second of uncompressed 1080p video at 30 frames per second requires about 180 megabytes of data. A 90-minute video at this rate would be a full terabyte of pixel data. In contrast, the high-definition videos you stream over the internet are usually less than 1/500th of that size. To achieve this level of compression, codecs don't just use one trick. They are a product of decades of algorithm development and ever more powerful encoding hardware. But for practical purposes, we can think of codecs using two complementary approaches, and together they give us our final compression ratio. Understanding this will help you choose the right codec and encoding parameters. If we pause a video on one of the frames, we can see that there are a lot of regions in the image where nearby pixel values are almost exactly the same. If we divide the picture into a grid, many of the grid cells have patterns that are easy to store with significantly less data than what is required for the pixels within. For example, in this block we can replace a large area with just a single color. Areas of the image with more detail are split into smaller blocks until they match one of the patterns programmed into the encoder. When video is coded this way, each frame is a self-contained picture, and the player can jump anywhere in the video and draw that frame immediately. You can also cut any part of the video without affecting the rest of the frames. Codecs where the frames are independent of each other are great for editing workflows. If you want to use them, use whatever is best supported by your editing software. But these codecs are quite inefficient. Videos they produce are great for local work, but impractical to stream over the internet. So we need a way to compress the video even more. If we bring back the grid from earlier and place it over two neighboring frames, we can see that although the picture as a whole is different, some of the individual grid pieces have not changed at all from frame to frame. For any unchanged region, we do not need to store the pixels again. Instead, we just reuse the same blocks from earlier frames. Often areas of the picture are not exactly the same between frames, but still very similar. Here the codec can store a transformation that just moves the pixels around a bit. So the encoder can save a full picture once and then save much smaller set of instructions for the frames that follow. These full picture anchors are called keyframes. When you seek in the middle of the video, the decoder starts from the nearest keyframe to your seek point and works forward until it reaches the frame you asked for. Encoders usually place keyframes on regular intervals and also at scene changes, where one frame stops predicting the next. From this structure, you can see the clear size wins. Keyframes are expensive because they contain the whole picture data, but the frames between them can be tiny. But editing this structure is difficult. If a keyframe is removed, all the frames until the next keyframe become invalid. This is why most editing software re-encodes the entire video for any kind of edit, even though for simple cuts and trims, it's a very wasteful process. Specialized video cutting tools analyze the frame structure around the cut and can avoid this re-encoding. Even though making the frames depend on each other has its downsides, this technique is really what makes video content on the internet possible. Pretty much all videos are encoded this way, and probably using one of these three codecs. If the video codec decides the picture quality, why does your editing software make you pick from a massive list of containers? Why can't we just make one universal box and put whatever video data we want in there? Well, actually, there is such a universal box, Matroshka or MKV. MKV files have almost no rules. They happily hold any video or audio, embed custom subtitle fonts, and even arbitrary file attachments, all in a single file. But this lack of limitations is exactly what prevents MKV from being widely supported. TV or smartphone manufacturers are not going to add support for a container that doesn't have a strict specification. .mp4 is the closest thing to a universal standard. It has wide device support and enough features to cover all normal use cases. Most other containers exist to serve one interest group or another. Apple develops MOV container because it's tightly integrated into their ecosystem. Google made WebM for the browser because royalty-free standard benefits both Chrome and YouTube. In the end, your editor has to show you the list of containers because it doesn't know what you are going to do with your videos. So the container choice isn't really a creative decision. It's a question of compatibility and which ecosystem you are in. Now that we know how video formats differ from each other, let's look at an example of how to choose the right format. When shooting footage, you need a format that won't instantly fill your camera's storage. So you want to use the best and most compressed codec supported by your device. Most commonly today, this is HEVC in MP4 container. But when you drop that file into your editing software, HEVC's heavy compression becomes a liability. So your editing software creates a proxy media, temporarily swapping out the complex source for much simpler intermediate codec. When the edit is finished, you export the video into H.264 inside an MP4, the format every platform accepts. It's small enough, quick to upload, and ready to play wherever it lands. Finally, YouTube takes that file and optimizes it for delivery over the internet. They don't care about editing, they only care about bandwidth and costs. So YouTube transcodes your video into incredibly dense, royalty-free web codecs like AV1 or VP9. And they also chop the video into tiny chunks so your smartphone can seamlessly change the quality if connection is bad. Same footage, 4 different formats, each format defined by its codec and container, each one serving a specific function. However, every time you recode a video, the compression errors compound and the picture quality gets a little bit worse. So for the best possible quality, you want to avoid recoding as much as possible. To cut and trim videos without re-encoding, you need Smart Media Cutter. quickly edit hours of raw footage with automatic speech detection and transcript-based editing. The paid version also includes powerful features for video professionals and enthusiasts, such as visualization of packet data, group of pictures, and reference frames. Download for free from smartmediacutter.com for Windows, macOS, and Linux.